Hi and welcome to my series on solving the wave heat and Laplace equations. This is the second last video in the series, and in this video we'll be solving the Laplace equation or the steady state heat equation with some Neumann boundary conditions. In the final video I'll go through what to do if we have inhomogeneous boundary conditions. As a prerequisite, as always, you should be familiar with solving first and second order linear ODEs, and preferably you've been introduced to the concept of PDEs as well. So the first thing we always want to do is to interpret what the question is asking. So in the Laplace equation, we actually have four boundary conditions and we don't have any time variables here. So we actually just have two spatial dimensions, x and y. And you can see that our y goes from 0 to 1. So I'll put a 1 here. And our x goes from 0 to 2. So we actually have something that looks like this. And here, I might write this in a different color, we have u equals 0. Here we have u of y equals 0. Here we have u of y again equals 0. And here we have u equals cosine pi y. So we have these boundary conditions, and there are four of them. And the Laplace equation is also known as the steady state heat equation, and that's because the temperature at different parts of the solid, so if this is our solid here, the temperature at different parts of the solid remains constant over time, so there's no time variable. Step 2. We can assume the solution to the PDE takes the form of u of little x little y equals big X of little x big Y of little y. Now if we sub this back in to the PDE, this gives us x y double prime plus x double prime y equals 0. Step 3 is to use separation of variables, which I'll just write SOV for short. Now the reason we assume the form u equals x times y is because that allows us to use separation of variables. So if we use separation of variables, we're just putting all the y variables on one side and all the x variables on another side. In this case, we're going to put, there has to be a negative sign on one of the sides. Because y up here has our two homogeneous conditions, then we're going to have the plus side for the y, and we're going to put the negative sign with the x. So if it was the other way around, then I'd put the negative sign with the y, and I do that in the previous video. Now because x and y are completely independent of each other, but yet they equal each other, we know that they have to be equal to a constant, and we'll call that constant k. But we also know with k is that it can be equal to negative lambda squared, and that is simply because k greater than 0 gives only trivial solutions for Neumann conditions and Dirichlet conditions. So we know that our k must be either equal to 0 or negative. Now if we rearrange this, we get two ordinary differential equations. So we get y double prime plus lambda squared y equals 0. And we also get x double prime minus lambda squared x equals 0. So the reason that we place the negative sign here with the x is because then when we're rearranging, that eventually will give us this negative sign here with the x. And all that does is ensure that we actually have a positive sign with our y, because we're going to work on this first. And that just means when we're doing the wave equation, the heat equation, and the Laplace equation, we're always doing the same things for at least the first half of our workings. It just ensures that we're less likely to make an error. So step 4, we want to use the two homogeneous boundary conditions with y double prime plus lambda squared y equals 0. And I know we have 3 homogeneous boundary conditions, but I mean the 2 that are associated with the same variable. So in that case, it's our y variable. So we're actually going to have 2 possible signs for lambda. We're going to have the case where lambda is greater than 0. We're going to have the case where lambda equals 0. And lambda can't be less than 0 because it's equal to, k is equal to negative lambda squared. So if we take the lambda greater than 0 case, we have the ODE plus lambda squared y equals 0. Now the general solution takes the form big Y of little y equals a cosine lambda y plus b sine lambda y. So that's just solving an ODE. Now, because we've got Neumann boundary conditions, we are going to want to take the derivative of that. So we're going to get negative a lambda sine lambda y plus b lambda cosine lambda y. So if we plug in one of our initial conditions, so if we go, boundary conditions, we are working with this one, these ones over here. So we'll first plug in the case where y equals 0, and then we'll plug in the case of y equals 1. And both of those have to set the equation equal to 0. So let's say this, where y equals 0, we are going to get simply b lambda, and that has to be equal to 0. And this just implies that b equals 0 because in this case our lambda is greater than 0. So if then we keep this b equal to 0 and now we plug in y equal to 1. So if we come back to this equation here, now b is equal to 0 and x is equal to 1, we get negative a lambda sine of lambda, and that has to equal 0. Now we could just say, well, this works if we let a equal 0, but if both a and b equal 0, we're just getting the trivial solution, and that just tells us what is happening when nothing's happening. So we're not interested in the trivial solution. So what we need is for sine of lambda to equal 0. And we know when sine equals 0, it equals 0 when, if we set lambda equal to n pi, where n is an integer and it starts at 1, 2, so on. It doesn't start at 0 because lambda is equal to n here, and we're doing the case for lambda greater than 0, so we're starting at 1, 2. On the right-hand side, we'll consider the case where n starts at 0, or n equals 0. So this here is known as our eigenvalue. this lambda, and that is the value that lambda takes when we're not getting the trivial solution. And this allows us to write this x of n here equals cosine n pi y for n equals 1, 2. So all I've done is taken this equation here and plugged in our values, and I've left out the constant a. So a and b are constants here. I've left out the constant a, but you can include it here as well. And that's because a multiple of an eigenfunction is an eigenfunction. So this is an eigenfunction. So you can include the constant a, but you don't have to. So on the right hand side we have the ordinary differential equation y double prime equals 0, because lambda equals 0 in this case. This has a general solution of the form y of little y equals a little y plus b, where a and b are some constants. So if we then take the derivative, because we're working with Neumann boundary conditions, we just get a. And now if we plug in those boundary conditions where y equals, so y of y equals 0, we get a again, and that just has to equal 0. And if we plug in the second one, where y is equal to 1, we get, again, we just get a, which equals 0. So what we're left with, if we plug in what a is back into our general solution here, we just get b. So y naught of y equals some constant b. So what we can say is that the lambda equals 0 case is a valid case, and we already know this because we're working with Neumann boundary conditions, so that's always going to be the case. But what I'm going to do now is write our proper eigenfunction. Now we've taken into account both of the possible signs of lambda. So I'm going to write this as x of n equals 1, and I'm just calling b 1 because, as I said, a multiple of an eigenfunction is an eigenfunction, where we end up multiplying this again later on. So I'm just going to call it 1, but you could easily call it b as well for some constant b. So I'll say this is the case when n equals 0, and I will say this is cosine n pi y, and this is for n equals 1, 2. Now you might say, wait, if you plug in n equals 0 into cosine, you're going to get a 1 anyway, so why don't you just write them together? And we can write it as cosine n pi y for n equals 0, 1, 2. Now the only reason that you may want to write it this top way is because later on when we're getting the associated eigenfunction, our t of n, it may or may not have a case for n equals 0, and it doesn't always work when it comes to multiplying our x of n by our t of n. So for that reason, I keep them separate. So you'll see sort of what I'm talking about in a moment. So if we go to step 5, we now use the homogeneous boundary condition associated with the x variable. So we're going to use the ODE, our x double prime minus lambda squared x equals 0 now. And again, we need to consider the cases when lambda equals 0 and lambda greater than 0. So in the case for lambda greater than 0, our x double prime minus lambda squared x equals 0 has a general solution of the form x of little x equals a, the hyperbolic cosine lambda x plus b, hyperbolic sine lambda x. And now what's the condition that we want to work with here? So we want our homogeneous boundary condition associated with our x value, so that is this one here. So it's not a derivative, we just need to plug in x equals 0. So if we say now x equals 0, we just end up with a hyperbolic cosine lambda x, and this has to be equal to 0, and this just say implies that a equals 0. So what we can do is write our x of n of x equals the hyperbolic sine, and lambda was n pi, so we'll write n pi x, and this was the case for n equals 1, 2, so on. Now on the right hand side we get the ODE x double prime equals 0. The general solution for this just equals x of little x equals ax plus b, and if we plug in x equals 0, we just get b equaling 0. So therefore our x naught of x, that's our case when n equals naught, just equals some constant b. Step 6 is we want to write these. Write u of n x y equals x of n x times y of n y, and we also want to do that for the case when n equals 0. Equals our x naught case of x and our yn of y. So when we come back here, you can see that in this case we are going to separate these two here for our n equals 0 and our n equals 1, 2, so on case. And that's because it's not going to work if we just write this and then times it by this x of n case over here. Oh, I've accidentally written x of n here. This should be y of n. I'm too used to doing the x's first and then the t's. Right, so for step 6, we're going to write u of naught of x and y, and all that is some constant b times with some other constant. Here I've just called it 1, but it could have been another b. All it is one constant multiplied by another constant, so we're just going to give that constant the name of a naught, and that's for n equals 0. Now for our u of n case, x, y, we're going to get the cosine multiplied with the hyperbolic sine, so we're going to get cosine n pi y multiplied by the hyperbolic sine of n pi x. Now we need to add a constant in here that we're going to call a of n, and that's just because, as I said, the multiple of a eigenfunction is an eigenfunction. So we need to add a constant here, and then our job is to find out what that constant is. So, and we can just write here, so that's that, and that is for some constants A0 and A_n. So our step 7 is to use either U0 or U_n. In some cases you'll have to use both, but in our particular case it will just be one, and that's because we've just got one term in our non-homogeneous boundary condition here. If we had something like 1 plus cosine pi y, then we would need to use the both the U0 and the U_n case and the superposition principle. Maybe see one of my other videos for that if you're interested. I'll put the link up now. So what we're doing is use either U0 or U_n to solve for the inhomogeneous condition. So our inhomogeneous condition was this, u of 2y. We can set that equal to our U_n case when x equals 2. So all I'm writing is our U_n and putting 2 for the x's. So we get A_n cosine n pi y hyperbolic sine of n pi 2, and that we set equal to what the actual inhomogeneous condition is, which is cosine pi y. Okay, so now all we're doing is we need to solve for n and A_n. And A_n needs to be constant. If A_n isn't a constant, then we need to go back and use the superposition principle to rewrite what U_n equals. We can see here if n equals 1, our cosines will match. And then to solve for our A_n, we're going to end up with A_n. If n equals 1, then our cosines match and we can divide by the cosines. So we end up with A_n hyperbolic sine 2 pi equals 1. And then just solving for A_n, we just get 1 over hyperbolic sine of 2 pi. So that's a constant, so we're all good and we don't need to rewrite our U_n. So we've got that. Now if A_n wasn't a constant, we would say something like this. Use the superposition principle to write U of n, x and y equal to A0 over 2 plus the sum of n equals 1 to infinity of our U_n case, which is A_n cosine n pi y hyperbolic sine of n pi x. And then we would solve for A0 and A_n using the Euler formula. So that's all we'd have to do in that case. I have another video where I do that. Right, so now the very last step, step 8, is to write the specific solution. In this case, we'll be using U_n. We don't need U0 at all. So U_n, n, and our values for A_n. So all that equals, we get U of x, y, It's no longer u of n because we know what n is. N is 1 in this case. So our a of n is 1 over the hyperbolic sine of 2 pi. And that's multiplied by cosine pi y because n is 1. And the hyperbolic sine of pi x. So that's our specific solution. So just to recap what we did, step 1 was to interpret the question. Step 2 was to assume the solution took the form of u equals x times y. That allows us to use separation of variables, which was step 3. Using that, we get 2 ordinary differential equations. We just make sure that the plus goes with the variable that has the 2 homogeneous boundary conditions, and we put the negative sign with the one that has an inhomogeneous boundary condition. Step 4 is we use the ODE with the 2 associated with the 2 homogeneous boundary conditions, and we consider the case for lambda greater than 0 and lambda equals 0. Because we're using Neumann boundary conditions in this case, our lambda greater than 0 is non-trivial, so we need to include that. It's step 5. We get the homogeneous boundary condition associated with our other variable. In this case, it was x. We need to consider the 2 cases for that as well. We have lambda greater than 0 and lambda equals 0. We then multiplied, step 6 was to multiply those x times our y to get our u, because we assume that in our second step, we assumed that the solution took this form, so we're just putting it back together in this form. Now, step 7 was to use either our u0 or u of n to solve for the inhomogeneous condition. In this case, we only needed our u of n, but if the inhomogeneous condition looks a little bit different, you may need your u0. We solve for a of n and n, and we just wrote what a of n and n was back into our u of n, and that's our specific solution. So not too difficult, and hopefully you enjoyed this video. If you found it useful, give it a like. If you found it really useful, subscribe. I make videos weekly, more often than not multiple times a week, and I cover maths, psychology, statistics, physics, astrophysics, all the fun stuff. So thanks for watching. Hopefully this wasn't too tedious for you if you don't enjoy maths. I don't think anyone enjoys doing all the simplifying up here. I certainly don't. Give me a thumbs up if you thought this was helpful. If you thought it was really helpful, subscribe to my channel. I aim to upload videos at least every week, if not more. Yeah. Thanks, and hopefully see you all in another video.